Today, let's take what we've learned about the rate law and go through some sample problems where we get to put into practice what we have already learned. So here's sample problem B, and 3 experiments that have identical conditions were performed to measure the initial rate of the reaction. And this is the reaction that took place during the experiment. We have hydrogen iodide decomposing to form hydrogen gas and iodine gas. The results of the 3 experiments, in which only the hydrogen iodide concentration was varied, are as follows. So here's our data table. In experiment 1, we began with a concentration of hydrogen iodide of 0.015 molar, and it was timed, and they measured the number of seconds that it took for this reaction to occur, and then they took the 0.015, divided it by the number of seconds, and they get the rate on the, and so that would be the number of moles per second. And then in the second experiment, they had double the concentration from the previous one and measured its rate. And then for the third experiment, they had tripled the original rate, or original concentration, I should say, and got a different rate. So we are supposed to write a rate law for this reaction, and we're going to find out the value and the units of the specific rate constant, the K. We're going to try to find out what is the actual value of K. So this is going to be the general rate law for this reaction. Remember, we always start out with a capital R, which indicates the rate, equals a K. It always has a K. And then we list the reactants. This only had one reactant, so we'll put the reactant in brackets, HI, and our job now is to figure out what the exponent is. What's that N? So in order to do this, what we do is we pick 2 of the concentrations to find out how the concentration has changed. You can pick any combinations you want. I would suggest that you, when you do these, that you put the concentration of the larger concentration on the top and the smaller concentration on the bottom. So we want this top number right here to be larger than the bottom number. If you do it the other way, you deal with fractions, and you know how most people are with fractions. They don't deal well with them, and so this is my suggestion to you. So from your data table, you'll notice that both 2 and 3 could have been used here, but they chose 2 and 1. And we notice that the concentration of experiment 2 was twice as much as the concentration in experiment 1. So this is our concentration ratio right here, and it gives us a value of 2. In other words, it says that the concentration has doubled. Then we use the same 2 experiments. You can't change to a different experiment. Now we have to use the same 2 experiments, and we're going to put the rate of the second one over the rate of the first. So this trial that you're trying down here for rate, which is number 2, has to be on the top because up here it was on the top. And then trial 1 is on the bottom, like trial 1 is on the bottom over here. So that's very important that you do that, otherwise you won't be able to see what you need to. And these are the rates right here that we got directly from the experiment. That's the rate when in trial 2, and this was the rate in trial 1. And when I divide one by the other, I find out that it is 4. So the rate is 4 times as much in 2 as it is in 1. So it's going 4 times faster than it is in 1. So if it's 4 times as much, what do I need to do is the real question you need to ask yourself. What is the question? What do I need to do in order to go from 2 to 4? Guess you can hardly even see that. Well, what do I do to 2? I could take it times 2, but we're looking at to what power. So is 4 2 to the first power or 2 to the second power? And this concentration at the top is this concentration right here is 2 to the second power to give us the 4 for the rate. So that's why we decided that 2 to the second power, that's why that exponent there after the HI is going to be a 2, because 2 squared is going to be 4. So this rate over here, the R, is equal to the concentration. That was, you could pick each one of these, whatever you wanted up here, and put it in here, and then it was squared. Now that we know that, we can calculate what K actually is. Now, if you take the original equation, which was R is equal to K times the concentration of hydrogen iodide squared, and solve for K, then we will get this equation right here. So to get the hydrogen iodide concentration to the other side, I will have to divide both sides by HI squared. That will leave me a K by itself, so R divided by this. Now, the question might be is, now what numbers do I put in here? And the key on this to remember, very important thing to remember, is this concentration and this rate and this concentration has to be for the same experiment. You can't pick one from one experiment and one from the other experiment. They have to be from the same experiment. So this looks like to be, I think it's trial 1. So this is the concentration of the hydrogen iodide in trial 1, and this was the rate of trial 1. So if I take 1.1 times 10 to the minus 3 on my calculator, divided by 0.015 and then square, don't forget to square it, then I will get this number right here. I got 4.9. Let's probably have to round it to 2 significant digits since this has 2. 4.9. Okay, that's the easy part just with the calculator. Now we have to do the units. And we have to look over here. We have an M on the top, capital M on the top, and on the bottom we have an M squared. So if we have M over M squared, we know that that will reduce down to 1 over M. And so we write all of these up here. We don't put any of them in the denominator. If it's in the denominator, I say that by indicating that it's a negative 1. So 1 over M is the same thing as M negative 1. 1 over M is the same thing as M negative 1. And then the other thing that sometimes is not as obvious to some people is when I write M slash S right up here, this S actually is on the bottom. It's actually here on the bottom. So that's 1 over S. This is the same thing as 1 over S. So over here, I'll write S negative 1. So now we have determined the value of K, and it's 4.9 M negative 1, S negative 1. And so I could put that into my original equation, R equals K, but in place of K, we're going to put 4.9 M negative 1, S negative 1, and I could put in any concentration for the hydrogen ion, come up with my own concentration, and I could predict at the rate of that chemical reaction, how fast it would go. So that's the beauty of this equation. We can actually predict how fast a new equation will go, because that's what laws do. They help us predict new information. Now let's look at another sample problem. Again, we have 3 experiments. They were performed to measure the initial rate of the reaction. And here they're not telling us what the actual reactants are. They're just telling us that reactant A is reacting with B and in the process forming something new called C. Okay, so that's all we know about it. They didn't give us the actual names, but it's not really important that we know what they actually are. The conditions were identical in all 3 experiments. In other words, the temperature, pressure, all the things that could possibly vary a chemical reaction. There were no, we didn't add a catalyst one time and not the other. So all the things that can cause a reaction to go at a different rate were held constant. Okay, so the only thing that was varied is the concentration. So the temperature wasn't varied, the catalyst and the identity or anything like that. Things that we've talked about early on in this chapter. And here is the data from that experiment. Now let's look at this data table a bit. We have 3 experiments, and in experiments 1 and 2, you'll notice that the concentration of A did not change from experiment 1 to experiment 2. But the concentration of B was allowed to change. In experiment 1, we have a concentration of 2.4 for B, and in the second one we have a concentration of 1.2. So they're not the same. Then we can look at one other thing here, which is because we can only look at one variable at a time. We could also see that when I compare experiment 1 with experiment 3, I'm going to compare these two right here, you will notice that A changes, but B does not. So notice that between 1 and 3, the concentrations were the same. But between 1 and 3, the concentrations of A changed. So it's kind of important to notice those patterns here, because that will be very important in helping us write this rate law. So we're going to write the rate law for this reaction. Then again, we're going to find the value in the units for our specific rate constant called K. So here we first write our generic or general rate law for this reaction. We have R equals K. It always begins with that. Then we list the the reactants. This one has 2 reactants. The previous one had only 1. This one has 2 reactants, A and B. And our job now is to figure out what are the exponents. What's the exponent of A, that N? Now we're going to try to find out what N is. And then what is the exponent of B? What's M? Now, to find M, now which one you work with first is really kind of up to you. In our slides here, we're starting out trying to find out what M is first. And we noticed to find out M, we're going to take experiments 1 and 2. Why? Because they have the same concentration of A. Okay, we wouldn't want to pick because we're looking for the, how B changes, then we need A not to change. So we couldn't try any other combination other than experiments 1 and 2. And so what we're going to do is we're going to pick the concentrations of B in trials 1 and 2, and you might notice that this time they have it B1 over B2. Why would we change it around? Why? Because we want the larger number to be on the top. The larger number on the top. smaller number on the bottom. Why? Because most people don't like fractions. And this will give us a whole number, or at least a number greater than 1. So between trial 1 and, trial 1 concentration is twice as much as the concentration was in trial 2. So over here we have the concentration of 2. Okay, now if you remember in the previous one, the next thing that we did is we looked at the rates. Now, how do we put them in the rate? Well, over here we had 1 on the top. We have to put the rate of 1 on the top. We can't switch it to 2 because that would mess us up. And then we're going to put the rate of 2, because up here we had the concentration of 2 on the bottom. We're going to put the rate of 2 on the bottom. And we picked the rates from the data table. These are the numbers that they gave us. And if I take this divided by this, you can probably do that one in your head, it is 2. So what does that mean? Well, that means if I double the concentration, I double the rate. If I double the concentration, I double the rate. This is like a direct relationship. Whatever I do to one, I do to the other. Now, if we had flipped these over, for those of you that don't mind fractions, we would have had 1/2 on the top for the concentration, and we would have had 1/2 for the rate. Well, again, that still is a direct relationship. If I cut one in half, I cut the other one in half. However you want to look at it, it's still. So this is a direct relationship, and we remember that when it is a direct relationship, then M is equal to 1. M is 1. And so the reaction is a first order for B. So B is a first order because M is equal to 1. Okay, so we figured out what one of the exponents is. Now we just have to figure out the other one. Now, to find N, we have to pick experiments 1 and 3. Why? Because we need to have B stay the same. So if you look at your data table, you'll notice that B stays the same between experiments 1 and 3. I kind of pointed those out when we were looking at the data table. Okay, so we're going to take the concentrations again, and notice this time we're picking the concentration of A for the third trial over the concentration of A for the first trial. Why? Well, because we need to do 1 and 3, but why did we put 3 on the top and 1 on the bottom? Why? Because we want the larger number to be on the top, so we get to deal with whole numbers. So we're going to have, this is the concentration of A in the third trial, this was the concentration of A in the first trial. And if I divide this by this, I get 3. That means the concentration between trial 1 and trial 3, the concentration was tripled, 3 times as much. Now the next step again is the same thing. We're going to look at the rates. Now, what rates do we put on the top? Well, over here, to get us to have the whole number for the concentration, we put 3 on the top. Well, that means we have to have rate 3 on the top as well. And concentration of A for the first trial was on the bottom, so we're going to do the rate for the first trial on the bottom. So this number divided by this number comes up with 9. Okay, just putting that in your calculator, calculating out 9. So now what has happened? If I tripled the concentration, the rate now is 9 times as much. 3 to what power is 9? 3 to what power is 9? Well, it's 3 squared, right? 3 squared is 9. So we now know that the N is 2, because 3 to this exponent of 2 is 9. That means this reaction is a second order in A. A second order in A, why? Because N is equal to 2. So now we can write the rate law because we have now the N and the M both determined what they are. And the rate law is R is equal to K times the concentration of A squared times the concentration of B. And we said it was a direct proportion is N is equal to 1. You don't have to write the 1 up there, but if you like to, you can. Remember, it just anything raised to the first power is the same thing. So now let's calculate out what K is equal to. So again, we're taking the R equals K times A squared times B, and we're dividing both sides by A squared B to get K by itself. Just to re-emphasize what we did in the previous example, it doesn't matter which of the trials you use when you get to this step. The only thing is all this information must be from the same trial. This has to be the same trial. So we have this for the rate, this for the concentration of A, and notice that we have to square it right here. Don't want to forget to do that. And then this is the concentration of B. So if I'll take 8.0 times 10 to the minus 8th divided by 1.2 squared divided by 2.4, I come up with this number right here, 2.3 times 10 to the minus 8. Okay, so that's just straight calculator work. Now we need to get the unit parts over here. Okay, so for the time being, let's just ignore all the number parts. On the top we have M. On the bottom we have M squared times M, so that's M cubed. So M over M cubed is the same thing as 1 over M squared. In other words, these two M's would cancel out. I'd have M squared on the bottom. So over here, 1 over M squared is written like this, M to the negative 2. Then the S, the same thing we said in the previous one, is really belongs on the bottom. It'll be S negative 1. So in almost all of these K's, it'll end in S negative 1 because they're always per second. Now let's kind of look at maybe like our first exception that we want to deal with. The form of the rate law depends on the reaction mechanism. Now, for a reaction that we've been talking about, they all occurred actually in a series of steps. And we said for that, then we have to do the experiments to be able to figure out what the exponents are for each of the concentrations. Well, it turns out that for a reaction that occurs in a single step, so this is the important thought right here. If it happens all in one single step, the reaction rate of that step is proportional to the product of the reactant concentrations. You're just going to multiply the concentrations together, but here's the part that's different. Okay, each of is going to be raised to its stoichiometric coefficient. So from our balanced equation, we can actually figure out what the exponents are going to be. So in this particular one, we had A reacting with B, forming 2C, let's say. That's a little bit different than what it was stated in the previous one, so it's not exactly the same example, but the two reactants are A and B, and there are no exponents in front of A or B. So the rate law is just going to be R, and this is going from left to right, so we call that forward, is going to be nothing more than R equals K times the concentration of A times the concentration of B. There are no exponents. They're just directly related. The rate of the concentration of A is directly related to the R, and the concentration of B is directly related to R. So there's, in this one, the fact that we could put coefficients up there is not shown down here because they don't have any coefficients. Now let's think of this reaction going in reverse. Uh, so in reverse, this is what it looks like if we wrote it in reverse, where we had a forward uh, facing reaction. And this reaction rate is the reverse of the previous one, as I said, but it's directly proportional to C times C. This 2C is the same thing as C plus C. And we have to list all the reactants, and this has two reactants. They just happen to be the same. So this 2C up here is C times C. Now, C times C, we could have written C with an exponent of 2, because we said we could, if this is a single step, we could write it as an exponent of 2. But C times C is the same thing as C squared. So the reaction rate in reverse is K for the reverse reaction. So this is different K than the other K, because we're talking about actually a different reaction. They're related to each other, but they're different, is equal to, and we could have written here C times C, but it's a little simpler for us to write just C squared. So that's kind of a different slant on some of these, but the only reason why we can do this is because this happens to be completed in a single step. So unless they say it happens in a single step, you follow the normal pattern that we've tried for problems B and C. But if they say it's in a single step, then you don't have to do the experiment part and figure out the concentrations and the rate. You can write it directly as it's shown right here. Tomorrow we'll kind of finish up the chapter.